Good morning. This is Ms. Billerbeck, and we are going to talk about 8.5 linear, exponential, and quadratic models. So delta is going to be my symbol for difference. That's what you'll see when you do calculus. It's a very nice abbreviation for the word difference. So I have x, y, and first delta or first difference. So here are my x values, here are my y values. So I want to see the delta of the y values, the output, not the input. So I'm going to take 1 minus -1. So 1 minus -1, and that equals 2. I don't have anything to subtract from this one, so this is going to be blank. So then this is 3 minus 1. So 3 minus 1 equals 2. And 5 minus 3, 5 minus 3 equals 2. So if we see here, we have 2. So our first difference is constant. Okay, so when the first difference is constant, that the best model is linear. So now let's look at this one. We have our input x values. We have our output y values. We see with the first difference, or first delta, will be 9 minus 3 equals 6. Again, there's nothing to subtract. So this is going to, from this 3, we have 3 minus nothing. So we can't do that one. So that's blank. So 9 minus 3 is 6. 19 minus 9 is 10. And 33 minus 19 is 14. So that's not a common difference for the first difference. So let's check the second difference. So we have nothing to subtract from the 6. So not only is this blank, but this is blank. So 10 minus 6 is 4. 14 minus 10 is 4. So the second delta is constant. Okay, so when the second delta is constant, the best model is a quadratic function. So now let's look at something like this where we have an input here and an output here. So when we see a pattern like this where 2 divided by 1, 2 divided by 1 equals 2, 4 divided by 2 equals 2, and 8 divided by 2 equals 2. We have a common ratio. And when we have a common ratio, that means the best model is going to be the exponential function. All right, let's take a look at some practice problems. So we're going to look at this. We look at, if we look at -5 minus a -2 for our output line, we see that that's -5 plus 2, which is -3. Our next one's -14 minus -5. So that's the same as -14 plus 5, which is -9. So then our next one will be -29 minus -14. So again, two negatives act like a positive, and programming, it just gets you to the exact same location, but backwards. So that's a long story, but -29 plus 14 would give us a -15. And then we have one more, -50 minus a -29 gives us, and that's going to be -21. So this is not a constant. Okay, so we have to look at the second difference now. So the second difference, we're going to write -9 minus -3. So that's -9 plus 3 gives us 6. Then we have -15 minus -9. That gives us, oh, I'm sorry, that's a -6. That gives us a -6. And then we have -21 minus a -15, and that also gives us a -6. So we have a constant second delta. So the best model is quadratic. All right, so it's definitely not linear because the first delta was not constant, but the second delta or difference was constant. So we have best model as the quadratic. All right, so when we look at this and we see, hey, that's going to infinity and beyond very quickly, that's something that seems a lot like an exponential. So instead of doing all this work first, let's start with the ratios. So the ratios, you put that number over that number. So 12 over 4. So the next number over the previous number. So that equals 3. Then we have 36 over 4, which is, 36 over 12. So 36 over 12, which is also 3. Then we have 108 over 36, which also is 3. And then we have 324 over 108, and that is also 3. So we have a common ratio. And that means the best model is exponential. All right. Let's take a look at another equation for a real life model. So this is data that has been collected in a real life situation. So data from a real life situation is not going to be exactly perfect. So when we do 89.5 and we subtract 100, we get -10.5. When we take 78.5 and subtract 89, that's 78.9. $89.5, that gives us -10.6. When we subtract 60, or when we subtract 68.4, we subtract 78.9 from it. So that gives us -10.5 again. And then we take 57.8 and we subtract 68.4 from it, and we have -10.6. Now, if we add this all up and divide by 4, we would get an average first common difference of -10.55. So that's an average of all these. These are very close together, and for a real life situation, they're practically the same. So when they're practically the same, you probably want to take an average and get a number like that. So this is going to be the average of the change. So it's how it changes, which when we find how it changes, That's the slope of a linear equation, because this is the first delta or difference. So this is linear. Okay, since we have a linear situation, we also know we have a y-intercept. And it is at 0, 100, because x is 0 at the y-intercept. So now if we're going to use an equation y equals mx plus b for a linear equation, we can write y equals, the change would be negative 10.55 x, and then it starts at 100. So we write 100. And that would be the equation that would best model this data. Okay, now that's how you do regression very quickly using that data. Okay. And I'll explain regressions a little bit more with you after the next example. All right, so let me share screen. So first we're going to compare. Let's talk about what we are going to do. We're going to compare the functions f of x is 3x plus 2, a linear function. G of x is 2x squared plus 3, a quadratic function. And h of x equals 2 to the x, an exponential function. And we want to show that as x increases, h of x, the exponential function, will eventually exceed f of x and g of x. All right, so let's go to the Desmos. All right, so first we're going to put in y equals 3x plus 2. So we have a line. That's our linear equation. Now let's put in g of x equals, now I should have called this f of x. So let's stick with what the book says. Whoops. I guess I better complete this before I move on to the other one. Okay, so we have 2x, and when we want it up, we hit the caret key, and it that's shift 6 on the keyboard. And then you arrow off that exponent so you can put in your plus sign. Otherwise, it ends up with your exponent. And that's, whoops, I didn't mean to go that way. So let's do plus. It wanted me to put a subscript in there. Okay, plus 3. So we have that. Let me see if I can get rid of that little subscript thing. Not. Okay, well, oh, it doesn't like that, so there, got it. So now we have a parabola. Okay, let's go back and make this f of x. Oops, that was FC, wouldn't like that, so x, there you go. Typing is an important skill. Okay, so let's do h of x. And we don't need a space, and we're going to do 2, and then x is going to be up there. Well, look at that. So we see that the line is above this exponential for a great amount of time, and the parabola is well above this exponential too. So when we look at that right here, finally the exponential is greater than the line at 3.7, comma 13.15, but even overtakes the parabola eventually. That's what exponentials do. So see right about here, it's overtaking that parabola. Right in here. So about 6.4, and that's at the y value is 85.5. So exponentials go to infinity and beyond. So that is what all three of them look like. So we can see the green exponential right here is surpassing both of them. Okay, so let's go and take a look at regression formulas one more time. Or let's actually learn how to do them. So when we put in a table, you can put a table in with this. And then if you have various formulas, let me grab the data we had over here. So let's go back to the sales data. So I'm going to put in 0, and then over here, I'm not quite sure why it's upset. So let's put in 0 again. Maybe I put in a letter O instead of a 0. And then 730. And then you can put 1 for the next item. And we put in 850. 2. This would be 930. And 3, we had 951. This is really a cool thing about Desmos here that I'm about to show you. It's very powerful. I like the graphing calculator because it's specific, but this is, as far as points, it's easier to get points off the graphing calculator. But this, when we put it in there and we put in a regular equation like y, and then we're going to do sub 1. And you just type 1, there's no special key, and then equals. And we want to find a quadratic, so we'll do ax 2. Oh, wait. I need a sub 1. Got to put a name there of sub 1, otherwise it won't work. So now we're going to put in the square, and then we will add bx, and then it's going to be sub 1. So you just type 1 and it puts it down in the subscript, and then plus c. Oh, you know what I forgot? This needs to be a tilde, not an equal sign. So look at that. All the statistics for this data. So we have the R pops up at 0.983, and it gives us all the parameters of the best fit equation for this. Okay, and if I wanted to see perhaps, does it fit that linear line? Because a linear model, I could put in this with a little tilde. Let's not forget the tilde, mx1, and then plus b. And look at that. It gives me the best fit line with the slope at 66.1 and b, my y-intercept at 762. Okay, this B, or C, was 736, which isn't too far from this for a y-intercept. So remember, the y-intercept for a quadratic is C, but for a linear equation, it ends up B. Okay, so that's the cool thing about how you can find line of best fit using Desmos. All right, so that's it for today. So I hope you have a wonderful day. Bye.